Good morning, everybody. Can you hear me back there? Does that work? Seems okay up here to me. I hope it's okay for you. Well, welcome to Psych 9A on January the 14th. Hope you're enjoying our Santa Ana winds out there. You know, I just read this article on these very deadly spores that fly through the air when the winds up in the Central Valley get high, and I'm just wondering if any of those spores are coming down our direction. Well, I hope not. Well, in addition to interesting weather, we have an interesting class today on research methods, and I don't know if you saw my first slide when I put it up very briefly. This has got to be one of the dullest subjects in the entire history of science. How do you actually conduct research to get important, valid results? Well, it turns out to be rather dull, but very important. So that's what we're going to be talking about today. Before I do so, I would like to remind you that discussion sections have started this week. How many people have already attended a discussion section? Wow, so you are the Monday people. Presumably you went over material from Chapter 1, and that will be the focus of this week's discussion sections. Good. We are going over Chapter 1 today in class, and I just wonder, did anybody actually look at Chapter 1 over the week? Oh, very nice, very nice. Remember, there's a recommended method. There is reading chapters 1 through 6, you know, in sort of an overview fashion, right at the beginning of the course, and then, before you go to a lecture on Chapter 1, reading Chapter 1. So, how many people have actually looked at Chapter 1 twice? Nice, very good. That's the way to do it, because when it comes time to take the midterm and final exams and to go on in life and know about things, well, the more exposure you have, the better you'll learn the material. So please do study this stuff. I want to talk today about research methods. I'm going to be leaving at 9:05. Why am I leaving at 9:05? I have a talk to give at 9:15 in another building. This is the first and last time that this will occur, and I apologize for this. But I've effectively got to shut all this down at 9:05, run to another building, and give another talk. And there is simply no way to avoid this problem. So if I start talking a little bit rapidly, it's because I want to finish as much of Chapter 1 as possible today. If we dribble over till Thursday, well, hey, that's no big problem. We can do some more on Thursday. I see a hand. Oh, I'm sorry, could you say that again? These are on the website. I put them up yesterday. Yeah. I generally try to get them up before the class. It's a good question. The links to our class videos are available on our class website also. So if you have missed a class already, or foresee yourself missing a class, or you'd like to see the lectures again at some later point, please go to our EEE website, click on the video link, and look at the very nice videos that are being made for you. How about more questions? Okay then. Well, I'm actually kidding a little bit when I say it's one of the dullest subjects, but it's not tremendously exciting all the time, I'll say that. The reason it's important is that if a person ignores the use of proper research methods, then they may potentially fall into, well, several traps that will produce research that is of little to no value. And BS here stands for an 8-letter word, and that's what happens when people ignore the use of proper research methods. So here's an example. It was reported in the New York Times 3 years ago, and the article is "Journal's paper on ESP is expected to prompt outrage." And you can go see this article if you want to. But there is this emeritus professor. An emeritus professor means you have a distinguished retired professor, namely an older person. And you'd be surprised how many emeritus professors decide that whatever they think turns out to be correct, and hey, we're going to tell everybody without censoring it as much as a younger person might. They're less careful about their careers. So here's an example of an emeritus professor, less careful about his career, who decided that, well, people can tell in advance whether or not they're going to be shown porn. And officially this is known as precognition for erotic photos. So effectively what you do is you have a person sit in front of a computer monitor and a picture would be presented, but before the picture is presented, you're supposed to say whether or not it's going to be a porno picture or not. And, well, if you do better than just sort of random guessing, then that means you're effectively telling the future, because you're saying which picture is going to show up next. And so that's an example of precognition, and if you haven't seen that word, there's a really good short story by Philip K. Dick, Minority Report, and it's also a movie. And you can see all about precognition there. In any event, how many people think precognition is sort of a real thing at this present time? Where you can sort of tell the future, you can sort of tell whether or not it's going to be an erotic photo or not. Well, I don't, and I think most people don't. And so seeing something like this is unexpected. So here's what they did, this guy. A software program randomly posted a picture behind one curtain or the other, but only after the participant made the choice, an erotic photo or not. And the participants in the experiment beat chance by 53% to 50%. By the way, if you have to guess whether it's an erotic photo or not an erotic photo, and you're just guessing, how many answers are you likely to get correct on average? 50%. It's like flipping a coin. You don't know whether it's going to be erotic or not, and so half the time you're correct, half the time you're incorrect. That's just guessing. So when you have 53% success, that's just a little bit more than the guessing rate, which is 50%. Now, it turns out that this effect is not found when the photos used are not erotic. So the first thing to note about this effect is that it's really small. 53% versus 50% is a tiny effect. This is something that you, as a future psychologist, should avoid. You want to find important effects that will establish your name in the annals of science for generations to come. Large effect sizes are good. 3%, that's trash. That's number one. If there are many human subjects who are running in an experiment of this sort, it's very possible that this very small effect, which is 3% better than chance, can be statistically significant. And it turns out there are methods in statistics that can be used to help you evaluate how likely it is a result can be found due to the operation of random factors alone, just due to chance. So effectively, statistics will tell you, well, in this experiment, it will be maybe in 4% of the experiments that you run, you will find a 53% guessing rate just by chance factors alone. And that might be deemed a statistically significant result if you've set your significance rate at 5% to begin with. So it turns out there's a really important principle here. If you keep on running experiments over and over and over and over again, it's almost certainly the case that you will get a statistically significant result just by chance. How many people have heard about the room full of monkeys writing Shakespeare's Hamlet? Have you heard about that one? Well, you know, if you give them a long enough period of time, those monkeys will do just about anything you can imagine, and if that period of time is long enough, they will write Shakespeare's Hamlet. Now, we all agree this is very unlikely, but if they have a nearly infinite piece of time, maybe they will. That's the whole idea behind sitting there doing your experiment over and over and over again. If you do them enough, you will get a significant result just by chance. And that's silly. You don't want to report a result that's due to chance operations. You want to report a result that's due to something more fundamental, something based on scientific principles. So, number one, you have a small effect size. It's almost certainly that this thing is not really true. And it's almost certainly the case that you would not be able to reproduce it. And there are journals out there that point out silly and bad research, and this is one of them. If you haven't seen the Journal of Irreproducible Results, already, then you should probably go take a look. That's a fun place. There's another fun site I sometimes go to. There are scientists out there, I think they're under a lot of career pressure, and what they do is they effectively lie and cheat when they write their papers. How many people have heard of publish and perish, or excuse me, publish or perish? Yeah, effectively, a lot of professors, they've got to write these papers and see them published in a scientific journal or something like that, so that their careers advance. And some people, well, they sort of fudge a little bit of the data, or they Photoshop their scientific photograph, or they copy somebody else's result published 10 years ago. Anyway, there's a really, really nice result that tracks all of the papers that have been retracted in real time, all across the domain of science. And if you want to see that, well, it's just a wonderful thing. Social psychology tends to be rife with such things. People effectively not presenting the truth. You can't really do scientific research without paying strict attention to what is true. You can't fudge things. Okay, that was a digression. It's obvious, but I had to say it. I have to make this point now. The basic principle of statistics is the more observations you make, the more likely it is that you will observe patterns that couldn't possibly occur by chance alone, even though they are occurring just by chance. Now, how many people have seen the more modern version of the movie Casino Royale? Now, that James Bond movie, I don't know if you play cards, but there's this game, Texas Hold'em, and these people are playing this card game, and they have this one hand right at the end of the Texas Hold'em scene where you have this really hard to believe sequence of hands from one player to the next going around the table. So there's somebody has a full house, and they bet a whole bunch of money, but unfortunately the next person has a better full house, and so they're winning the hand. They bet a whole bunch of money, and then finally you get the guy with the straight flush, and the odds of such a thing are 1,000,000 to 1 at the very least. So the whole point is this sort of thing is very unlikely, but the more you play poker, the more likely it is that you will see these unlikely hands, these unlikely events. And it's just that way when you are doing psychological experiments. The more times you run an experiment over and over and over again, and you're running it over and over again because you can't get a result, finally, if you run it the 11th time, maybe you'll get some statistically significant result. But that's probably just due to chance factors alone. You shouldn't have run it that many times in the first place if you weren't getting a result. Does that make any sense? Okay, so that's an important thing. So let me turn now to observation and observed variables. What people tend to do in observational studies is to, say, look at something and study it without actually performing any experimental manipulation. And a good example is astronomy or cosmology, looking at the stars. At this point in time, at least, that's all we can do. We can look at stars. I guess we can measure the sun's output in different areas of the spectrum and things like that. But on the whole, we're not actually flying to stars and doing experiments on them. We are observing them through telescopes and other measuring devices of that sort. So if we are an astronomer, we're relying on observations. And what we typically do is build a science by finding examples of various phenomena and then saying, well, if we have a certain number of examples, maybe there's a general principle going on here. So we might find examples of what appear to be exploding stars, and this might get developed into a theory of supernovas and how certain stars can explode at various periods towards the end of their lifetimes. One thing you can do with observation in any field is to develop a hypothesis about what is going on, some causal scientific explanation of why certain things are happening. And if you're lucky, you're going to be able to perform an experiment that would test whether or not that hypothesis is true. If you are not lucky, maybe you're working in a field like astronomy, it may not be possible to perform an actual experiment simply because all your stars are way too far away. Turns out in psychology, we are lucky. We're frequently able to perform experiments on human behavior and behavior of other species. So, but there are other fields where you can formulate hypotheses based on observation, but never be able to test them, simply because the subject matter is too far away or some other reason. Now, another example is testing a hypothesis like this from economics. What we are going to do is give you an example of somebody who has developed a hypothesis based on examples and come up with something that is nonsensical. So, from economics, sunspots cause economic cycles. Well, what is an economic cycle, first of all? Everybody knows we're just leaving our Great Recession. Back in the 30s, that was the Depression. So you know that occasionally the economy is not doing that well. In fact, people talk about a business cycle, and effectively you can look at things like the gross domestic product, or basically the output of goods created in this particular country. That would be the US GDP. And you can see how big that is in each year. If you were to make a plot of that, well, you get something like this. This starts in 1923 and works its way up to 2008 on the right end. And it's a sort of a base level of productivity. And you can see now the fluctuations, more gross domestic product represented by blue and less domestic product represented by red. And you can see how these fluctuations work as time passes. And if you look, for example, at these red areas, you say, well, there's red, that's a recession, or in fact, this is a depression. This is not good. This is not so hot. And then a little bit more recently, you can see we have things in the late 60s, 70s, early 80s. And this is the point where I start remembering these. Early 80s, I just came out of college, and there are no jobs. Why was that? It was actually a very deep recession. Late 80s, early 80s, almost 90, almost 2000. There was a recession associated with those internet people crashing. And then more recently, we entered a great recession. What you can sort of see is that maybe every 11 years or so, on average, we are getting some kind of recession. So there's this sort of trend. It's not precise, but that's the idea. And this one fellow looked at this, and this guy's name is William Stanley Jevons. He looked at this business cycle in 1878 and said, aha, I know another cycle that goes up and down approximately every 11 years, and that is the cycle of sunspots. How many sunspots there are that you can see on the sun. And so this plot is now showing the number of sunspots, the sunspot number. And in the top panel, it starts at 1750. That's a long time ago. And in fact, there's some missing data. That's what the colors are indicating. It goes up to 1850. By the time you're at 1850, in the middle panel here, you go up to 1950, and you have all the data that you need. How many sunspots there are each year. It goes up and down and up and down and up and down, and through about 2014 or so. And this is an 11-year cycle, and so William Stanley Jevons suggested that, well, sunspots are causing our economic cycle. And you have to wonder about that. Is there any big reason to think that this is true? Can anybody think of any mechanism by which the sunspots would cause the economic cycle to behave this way? It's really hard to do so at the present time. I can't think of one. And most people would say, well, this is an example of two variables, namely the gross domestic product and the number of sunspots, these two variables that change in a highly correlated fashion. When one is up, the other one's down. When you have a lot of sunspots, well, the economy doesn't do very well. So there's a high correlation. Does that mean that one of these variables in some sense is causing the other variable to change? No. This is a great example of correlation does not mean causation. correlation does not imply causation, and it's one of the most important things to know about performing research. Just because you see two things are changing in similar ways, that doesn't mean that one of them is causing the other. And I'm going to return to this point at the end of today's lecture. In any event, that's probably the most famous example. This guy was wrong. Sunspots do not cause economic cycles. Okay. Now here is another subject that is difficult to perform experiments on, although it is possible. It is difficult with certain species, though. So in this case, we're considering a psychological hypothesis, namely Darwinian evolution has played a key role in determining human behavior. How easy is it to perform an experiment on that topic? Well, what we would have to do is manipulate people's genetic makeup if we were to perform a true experiment on this topic. And to date, we don't do that sort of thing. Okay? You'd have to directly manipulate the DNA inside somebody's body to study this directly by experiment, and that's simply not something we do. It is possible, and it has been done, to do these sorts of things with little insects, these poor little fruit flies or something. And there you can find evidence that yes, evolution does have a key role in determining behavior, but it hasn't worked its way up through humans yet. So this is an area that is very difficult to do experiments in. For obvious reasons, we cannot fiddle with existing people's genetic makeup as psychological scientists. Now, what about these experiments? These experiments really are the way to test hypotheses, and there are certain things associated with experiments that come with terminology. So the first thing you want to know about are independent variables, and these are variables that are directly manipulated by an experimenter. So let's say I want to do an experiment on how sensitive people are to different light levels. Well, one of the independent variables might be the brightness of the light's intensity. So you can sort of imagine I have a light bulb that has very few watts. I have a light bulb with some intermediate number of watts. I have a light bulb with a large number of watts. If you're doing an actual experiment, you'd be using more sophisticated things than light bulbs, but that's the idea. You can vary the intensity of your light stimulus. So in this particular example, the independent variable might be, well, the light intensity, and it would have several levels, like low, medium, and high. And you can directly manipulate these, you, the experimenter, simply by using a different light at different times in the experiment. So that would be an independent variable. You are in charge of how bright the light is. Now, what is a dependent variable? That is something that you measure. Well, I can give you one example. You can measure how wide somebody's pupil is. So if they're in a dark room, you've probably noticed that a person's pupil is pretty darn wide. If they're in a sort of medium grayish room, then it's sort of medium wide. But if they're in a very bright room or outdoors on a sunny day, pupils are very narrow. So what you could do is simply measure the pupil size as a function of how bright your light is. So your independent variable is the brightness of the light, its intensity. Your dependent variable is the pupil diameter. And you would find, aha, as we brighten the light, the pupil gets narrower and narrower. Now, there are dependent variables that are less physiological, of course, than pupil size. You could, for instance, have subjects rate their impression of how bright the light is. You could use a scale from 1 to 7, say, and they would have to assign a number to each light that you present them. And that number would be their judgment of how bright the light is. This would now be their subjective assessment of light intensity in your experiment. And this number that they assign, well, that's another example of a dependent variable. It's effectively the way that you are measuring your experiment's effect. And when I say your experiment's effect, what I'm really saying is the effect of varying the different levels of your independent variable. for instance, light intensity levels. Now, sometimes you need to pay attention to extraneous factors that might be influencing your results. Those extraneous factors that you sort of like to rule out when you come to explain your data are known as control variables. And you want to say, aha, I've got to control for certain things in my experiment if I am to come to a result that can be readily and validly interpreted. So for instance, if I am interested in light intensity evaluations, and I can imagine, say, 3 kinds of light bulbs, low, medium, and high number of watts, or different levels of light on a computer monitor. But I've really got to make certain that the lighting in the room where the experiment takes place is controlled. In particular, it better not be changing. If I have a window in this room and some of the subjects are doing the experiment at nighttime, then there's no light coming in the window. If there are other subjects doing it in the middle of the day, there's plenty of light coming through the window. What if a cloud passes over the sun? Then during the middle of an experiment with a single subject, the amount of light in that room is changing. This can influence a person's judgment of how bright the light source is. So you've got to control for the environmental amount of light. It's obvious, but you've got to do it. That would be an example of a control variable. Now, a subject variable is a characteristic of what is normally a human subject participating in a psych experiment. These are not directly manipulated by the experimenter. They are not independent variables. So, what's an example? A person's height. The person walks into your room, they want to perform as a subject in your experiment, and you're interested in their height. Is this an independent variable that you are able to manipulate? No. And in fact, manipulating somebody's height, that calls to my mind these very gory pictures. What are you doing to make that person shorter? Ouch. Okay, so we don't manipulate a person's height. What about gender, male versus female, say? Do we manipulate that? No. That's another example of a subject variable. Do we manipulate the color of their eyes? No. They're all sorts. Do we manipulate their native language? No. These are all things that a subject comes with into your experiment. You as the experimenter may be interested in the effects of these variables, but you as the experimenter do not manipulate them. So these are subject variables. A quasi-experiment, finally, is an experiment in which the effects of only subject variables are tested. Okay? So it's not a true experiment when you use just subject variables. Now, if one has one or more dependent variables, there will be data to analyze. And this is not a class on statistics. That may be good news for some of you. But statistics is a fact of life. And there are 2 kinds of statistics that you're going to want to be familiar with. One kind is called descriptive statistics. Then here, what you're simply doing is taking your data and describing them in a compact way. So for instance, let's suppose that you are interested in people's ratings of light intensity, and you have collected numbers 1 through 7 when people look at low, medium, and high intensity lights. So what we could do is we could say, well, what's the average number people give when they're looking at the low intensity light? Maybe it's 1.5. What's the average number they give when they're looking at the medium intensity light? Maybe it's 4. What's the average number the person reports when they're looking at a high intensity light? Well, maybe 7. We can figure out these numbers. So the mean, of course, is the 4-letter word for average. And what you do to figure out the average is simply add up your data and divide by the number of data. And this is all familiar from 7th grade or what have you. The median is the middle value. If you line up your data in order from the lowest to the highest, then you pick up the one in the middle. That would be the median. And the mode is the most frequent value. Now, it turns out that in addition to describing the central tendency, which is what the 3 M's do, effectively the center of your data, It's also important to describe how your data vary about that central tendency. And this is where the variance and the standard deviation come into play. Let's say we're talking about youngsters. And let's say I have two youngsters. And I'm going to tell you that the average age of those two youngsters is 5. And this might call to your mind a picture of two 5-year-olds. They would get along, they'd play together, whatever the 5-year-olds do. But, you know, just because their average age is 5 doesn't mean that these kids are both 5 years old. It could be that one of them is, well, let's see, what do we need to do to have an average of 5? The two ages have to add up to 10, because when we divide by 2, that'll give us the average of 5. So we could have a 9-year-old kid and a 1-year-old kid. Are they going to play together? I sort of doubt it. You know, so in the second case, there's a lot of variance about the age of 5. 1 is very different from 5. 9 is very different from 5. And what we can do is quantify that variance, come up with a number that says how much there is. And if we were to take the square root of that, well, we'd have the standard deviation. If you want to see examples of that, you can look in the textbook. You can also ask your TAs in discussion section. It will not be an emphasis of this particular course, knowing how to compute these. But it is very important. These are simple ways to describe data. Now, inferential statistics is when you're trying to draw inferences concerning whether or not your experimental manipulation produces results that really could not have occurred due to chance alone. They really are statistically significant results. So you're trying to draw some sort of inference about whether your results are any good, whether you have an effect. And the example I tend to think of in this context are people's heights, because it's a very obvious sort of thing. And the two sets of heights I tend to consider are the heights of the females in this classroom versus the heights of the males. Now, females alone. Is there anybody who is less than 5 feet tall? And it's okay to raise your hand. Please help me with this. Good. So we have a female who is less than 5 feet tall. Males. Are there any males who are less than 5 feet tall? Please raise your hand if that is true. I do not see a hand. Males, what about less than 5'3"? Okay, I see one. So it looks as though our shortest members of the class, the male versus female, difference might be on the order of 3 inches maybe. Males a little bit taller. Now let me ask, on the other end of the spectrum, females, anybody above 6'6"? Females above 6'6"? 6 feet 6 inches. No, what about 6 feet 3 inches? The basketball team is not in this class. Okay, what about 6 feet? Females above 6 feet? No, I'm missing a hand for 6. Oh, what about 5'9"? There are definitely females above 5'9". I've seen you. Good. Now, males above 6'6", above 6'3". Anybody? There we go. So I would say that when we look at the tall range, again, the males in this class appear to be taller than the females. And if we were to measure everybody's height in this room, what we would find, I think, is that we have males on average being maybe 2 or 3 inches taller than females. That's what I typically see when I do this in detail. Does that mean that if I were to randomly select one of you females and randomly select one of you males, that the male would be taller than the female? Is that what that means? No, it does not. Because there's tremendous amount of overlap between the heights in these two sets of individuals. There's a tremendous number of males and females who are exactly the same height. There are a tremendous number of females who are taller than I am. You know, the whole works. There's so much overlap between males and females, you have to ask yourself, well, is the average difference in heights, which might be 2 or 3 inches, is that something that is occurring due to chance alone, or is there some reason to think that this is a true thing, scientifically significant? So what do people say? Is that 3 inches a chance factor, or is there something else going on? Something else like maybe biological. Yeah, there may be different hormones that are causing different sorts of growth patterns that lead to males being, on average, a little bit taller, even though, of course, there's a tremendous amount of overlap in the two populations. So that is a guess that we can make, is that there is something going on here. But one thing we can do as a statistician is to look at the sets of heights for males, look at the sets of heights for females, and we'll find out that these heights overlap one another tremendously. And we can then use inferential statistics to tell us how likely it is that our height numbers, that our height data are due to the operation of chance factors alone. That's what inferential statistics does. What we find is if the difference between the two average heights is large compared to the variation in the measurements, well, if it's large enough, then we have a statistically significant result. If the difference in the average heights, and again, that might be on the order of 3 inches, is not large compared to the range, compared to the spread in people's heights, well, then we say it's not significant. And statistics will tell us what the answer is. If there is a small difference in the average heights, then you typically will need a larger number of data to ascertain that such a difference is statistically significant. You have statistical power to help you tell the difference. Now, back to experiments. We have our variables, we have some dependent variables providing us data. We can describe the numbers that we get for our dependent variable measurements. We can do some inferential statistics. Now we need to look at, well, how we design an experiment in a little bit more detail. It turns out that there are 3 basic sorts of experiment designs. And the first that we normally encounter is the between subjects design. And the levels of an independent variable are represented by different groups of subjects. And the standard example of that is like clinical or medical tests of various sorts. For instance, let's say we want to test whether or not a particular drug works. What we could do is take subjects in our experiment and assign them randomly to either an experimental group or to a control group. And what we would do is give the people who are in the experimental group doses of the drug that we're testing, and give the people who are assigned to the control group a placebo, not our drug that we're testing. And the idea there would then be to say, well, let's measure whether or not this drug is having an effect by comparing results for the experimental group of people to results from the control group of people. So that would be a between subjects design. The levels of your independent variable in this case are receive the test drug, do not receive the test drug. And so your independent variable is effectively test drug administration, yes or no. And your idea then is to randomly assign subjects to the 2 groups. Do they receive it or not? And you can then compare the 2 groups' data to see whether or not there's an effect of the drug. Between subjects design. Now you can also administer the levels of an independent variable to each subject in an experiment. And the example I had before, why don't I stick with that? This was our intensity of light example. And we have people come into a room and they will judge how bright a light is, and we will show them lights of different brightnesses. And remember that the independent variable in this case is the intensity of the light. There are different levels, dim, medium, and intense. And each subject gets to see each level of the independent variable. Each subject experiences the different brightnesses of the light. So that means we have a within subjects design. The levels of an independent variable are examined for single subjects. Each person in the experiment sees all levels of the variable. Now you can mix this up. And there are a lot of experiments with a mixed design, and a mixed design experiment must have at least 2 independent variables, and one of them's got to be a between subjects variable. And you will measure its effect across different groups of people. The other independent variable has got to be administered within single subjects, and so you will compare the results of single subjects to see whether that variable had any effect. So you've got at least 2 independent variables in that sort of design. Okay, so shifting gears now. I was talking earlier about correlation and causation. I want to return to that and first remind you about correlation. It's important to have an intuitive notion of what goes on when things are correlated versus when things aren't. So what I'm going to do is I'm going to point you to a Java applet, and I think I should have it, whoops, this guy, here it is. So this is a Java applet, and if I can get it to work, it will automatically do things like fit lines to data. And this is a good thing. So what I'm going to do is start adding data on this plot. The plot has a horizontal axis, and I think of the horizontal axis as telling us the value of a first variable. So the horizontal axis is telling us the value of a first variable, x, I don't know. And it's low over on the left and it's high over on the right. And you know, you can make this any variable you want to. If you're interested in sunspots and gross domestic product, this could be the gross domestic product. It could be low versus high. This could be grades in a class, if you're interested in more developmental psychology, low to high, something like that. Your second variable, its values are going to get plotted on the vertical axis. Again, it's going to start low here and then go up high to a high value. And that could be, well, the number of sunspots in any given year. And what we're going to do is plot points that indicate the 2 variables' value for each instance or element in our study. So we could examine years, and for each year, plot a point that says what the gross domestic product is. The same point will tell us what the number of sunspots is. So let me give you an example. Let's say I have a year in which we have a very low gross domestic product. That means I'd have to draw something over on the left. But simultaneously, I have a high number of sunspots, and that means I'd have to draw a point that's up here because this axis is representing the sunspot. So here's a point, and that point has effectively the ability to tell us that, well, here's a year where we have a fairly low gross domestic product but a very high number of sunspots. I'm going to draw the opposite kind of year now with another point. I'm going to say we have a very high gross domestic product. That means we're over on the right, but we have a low number of sunspots. That would be this point. And if I measured results from a whole bunch of years, then, you know, I might get something like this. Each point represents 2 numbers again. The horizontal axis tells us the economy. The second one tells us the sun. And let's say I get those measurements. Then we want to do things like, well, figure out how much correlation there is. And in this case, this is the great thing about this program. It says your correlation coefficient is minus 0.7, whatever that is. And what that means is, well, what does it mean? How many people sort of know how correlation coefficients work already? Good, good. Okay, let me give you an example of 2 variables that you know intuitively are pretty highly correlated. Height and weight. Now let's say a person is 2 feet high. Do we expect a large weight? No, this is obviously some small kid. It's not going to weigh very much. Now let's say we have a person who is 6'6". Do we expect a large number for the weight? You bet. Now I'm not saying that this is 100% correlated because clearly there are thin people and weighty people. There are short people, there are tall people, but there is some correlation going on here. So let me clear this, and what I'm going to do is consider my horizontal axis to be the height and my vertical axis to be the weight. And what we're going to do for each person in our study, we're going to get a data point that says what their height and weight are. And it's going to go like this. There will be a positive correlation between the two variables. As we increase height, we expect a concomitant increase in weight. That's a positive correlation. One of the things increases, the other thing increases. It's not a perfect correlation. There's spread in these points. The correlation coefficient is 0.69, which is a very high correlation. It's a positive number, which means that as one of the variables increases, so does the other, but it's not a perfect thing. If we had a perfectly correlated set of two variables, what would we have to have? All of our data would have to lie on a straight line. And that means all of my data would have to sit on a line like this. And if I drew this perfectly, my correlation coefficient would be 1. Instead, it's 0.999, but you know, that would be a correlation coefficient of 1. A perfect correlation between two variables. As one increases, the other one increases a set amount also. And that would be a perfect correlation, 1.0. Now, you don't really get correlations of 1.0 when you study psychology. You get correlations of the kind I showed you before. Let me do this again. And again, say height and weight or some other variables. There will be spread about some ideal line, and that spread about this ideal line that you fit to the data. This is the line fit to the data here. That effectively is telling you that your correlation is less than perfect. The correlation, in this case a positive correlation, is less than 1. Now, the first example I started with, in fact, had a negative number for the correlation, and that means as one of the variables increases, the other variable decreases. In fact, I think, let me do not show this line. There we go. Let me add some data points now. And remember, the example that I had here was, well, gross domestic product versus sunspots. And the idea is if we have a lot of sunspots, we have a low domestic product. With one of these things increasing, the other thing decreases. So the two variables are going in opposite directions. When the two variables change in opposite ways, you have a negative correlation. And you can see our number here is negative 0.8. That's a high correlation, but it's a negative correlation. What is a perfect negative correlation number, do you think? -1. So if I had all of my data falling on a straight line that was slanting down, and I'm going to draw that line, and now I'm going to add some data that sit exactly on that line. Hopefully I will get a -1, and my program tells me it's -0.9999, so that's close enough. Okay, so if your data are telling you that as one variable increases, so does the other, positive correlation. If your data are telling you that as one variable increases, the other decreases, negative correlation, negative number. What about 0? How do you get a correlation of 0? What does it mean for two variables to be uncorrelated? Well, it means that you have data that if one of them increases, well, you don't really have any idea what the other one is doing. And I'm not doing a very good job here. Let me see if I can get, okay, so those data points there give rise to a correlation coefficient of just about 0. So the two variables that are providing these data, well, you would say they're uncorrelated because the correlation is 0. If I were to fit a least squares line, you would find, among other things, that it is more or less horizontal. So if you look at your data points and you say, well, the line that goes through those data points is a horizontal line, well, too bad. Your psychological study did not work. You have 0 correlation. Okay, so your correlation coefficient, a large positive correlation is the value 1. Then it slides down to 0 for no correlation whatsoever. Then you have a large negative correlation that goes to -1. That's the range of correlation coefficients. Anyway, I like this little thing. I play with it. It's a good link. It's a good Java applet. Now, of course, Java applets are getting rarer because Java is one of the most popular ways to get malware on your computer. But if you can take that chance, I would definitely try out this Java applet. We're almost done what I want to say. Now, at this point, you could say, aha, I have an idea. I can measure correlation between two variables, and I can quantify it using a correlation coefficient that varies between -1 and +1. Does correlation imply causation? And the answer has got to be no. You've got to use your scientific thinking to help answer this question, though. It's not immediately clear that sunspots don't cause economic downturns, because what if sunspots were related to strong electromagnetic flares that travel through space to Earth and disrupts all the radio waves, and in addition to disrupting radio waves, it also messes up functions of the brain that make us work hard? You know, that's BS, of course, but you never know. So it's your sort of scientific judgment that sunspots are not causing economic downturns, but you're not 100% certain of it. So you've got to make a judgment here. There are other reasons that you might say one thing is not causing one another. And one reason is that there is a hidden variable which mediates the influence of one thing on another. For instance, does taking Latin in high school cause you to get good grades in college? Now, it turns out, if you were to do a little correlation plot of people who have taken Latin or not versus their grades in college, you would find that yes, taking Latin in high school generally leads to better grades in college. So you'd say, aha, there's a correlation. Does that mean taking Latin causes better grades? And most people would say, how is that possible? Now, what we would guess is that having high academic aptitude and motivation is a good way to get better grades in college. So maybe there's something going on here. For instance, let's say there's a hidden variable. In this case, going to an excellent high school that caters to college-bound students makes it more likely that this high school offers Latin, and that means it's more likely that a person takes Latin in high school. Simultaneously, the student who goes to this excellent high school is getting good college preparation, and that leads to better grades in college. So there may be this hidden variable, namely the excellence of the high school, that causes both a greater number of people to take Latin and a greater number of people to get good grades in college. So it isn't as though taking Latin causes good grades in college. No. It simply means that perhaps there was an excellent high school that led to both of those things occurring. So that's a third or hidden variable that sort of explains how two things that are correlated become related to one another, even though they're not directly linked causally, if that makes any sense. Research methods are something you want to learn about to make certain that the research you perform is excellent. And it's really got to be excellent in several ways. One of the first ways is to have a high validity. Validity simply means it's true in the basic sense, but it's a refined term when you think about research methods. In fact, people talk about two kinds of validity: internal validity and external validity. And internal validity refers to the logic and execution of the experiment with respect to the hypotheses that it was designed to test. So, let's say you have a hypothesis, which is that increasing the brightness of a light causes pupil constriction. And then you perform an experiment with an open window, and you perform that experiment at different times of day: nighttime, daytime, cloud in front of the sun. You know, that means you fouled up the experiment. You really should have controlled the level of illumination in the room where you're doing this sort of thing. That means that the internal validity of this experiment is 0. Okay? You'd say this is a poorly done experiment. There are all sorts of reasons why an experiment could lack internal validity. Your job as a designer of experiments is to test your hypothesis in a way that will lend your study internal validity. Make certain that you end up testing what you think you're testing. Now, there's a second kind of validity right here, external, which refers to whether your result has external relevance. Now, if you are performing a clinical drug testing result, this may have external validity in the sense that, well, the medical community has now learned whether or not this drug actually works. And if it does, that can have tremendous benefits for patients all over the world. If it doesn't, well, you know to avoid it. It's definitely a relevant sort of thing you want to know. It's also possible to have an experiment with very low external validity. And I'm sort of scared of coming up with an example from real life because the people who perform things with low external validity would be insulted. But you can imagine doing an experiment on something that nobody else cares about. Can you imagine something like that? Well, I can imagine something like that. It's hard for me to name an example. But these are basically experiments on topics that you yourself are interested in. They might be publishable in certain research journals, but they'll never see the light of day. They'll never show up on your favorite news feed. Nobody really cares. 6 months after publication, the whole thing is forgotten and you've moved on to something else. That would lack external validity. So it's really important then to have some external validity. You're doing something that has some current applications. Now you have to ask yourself, well, does all important science have external validity when it is first done or first accomplished? And the answer is no. There's lots of basic scientific research that does not look very applicable when it is first performed, but turns out to be applicable decades later. So it's a difficult thing, external validity. Okay, so validity is whether or not you're generating scientific truth that is applicable or interesting. That's effectively what those two things mean. Reliability is whether or not your experiment is generating consistent results. So examples will show what reliability is all about. Let's say you have the Olympics and you have a panel of judges and they all return the same score for an athlete's performance. 5.6, something like that. Everybody's 5.6, 5.6, 5.6. You would say, well, that's very consistent. All the judges are returning the same score. If they're all saying the same thing, then you're more comfortable in thinking that their score reflects the performance. There's a good amount of agreement in what the judges are saying. Now let's say the judge from one country is like 1.2, and the judge from the other country is like 9.8, and everybody's, then you know something's up, right? It's like these judges, somebody's, you can no longer trust the average score as much when there's a big spread in what the judges are saying. You'd say, well, they're not all that consistent. You would say, in the first case, we have a good amount of reliability, a good amount of consistency in our data. In the second case, you'd say, reliability is really low. There's a lot of inconsistency. This is rate of reliability is sort of consistency when you have multiple judges or multiple raters of something going on. Another kind of reliability you might be familiar with is test, retest reliability. So if you were to take the SAT twice, you might find that your score improves, but what they've shown is that it's unlikely to improve a whole bunch. Like it's unlikely to jump up millions of points. And the idea is that the SAT measurement is a reliable one, so that what you get in the first test is going to be pretty close to what you get on the second test. So that in some sense, the SAT test is reliably measuring this aptitude that it allegedly measures for people entering college. So that's known as test, retest, reliability. So validity then is telling you about scientific truth, both about what the experiment is doing and saying, and both in terms of its external relevance. Reliability is more a close examination of the data and saying whether your data are consistently telling you a certain story, or whether there's a large amount of disagreement. If your study has all of these features, then you're doing well. Both validity and reliability are needed for an excellent research study. That is what I wanted to say today, and I'm glad that I ended about 9 o'clock, because I'm now going to run off to this other building. I wish you a good couple of days. See you again on Thursday for a look at Chapter 2. And you know what to do. Read Chapter 2. See you.